Hello again, Physics 30s. In today's lesson, we are going to continue to apply the wave-particle nature of light, or the photon model. And this time we're going to look at something called the Compton effect and also look into an experiment called the Compton scattering experiment. However, before we do that, we're going to talk a little bit about X-rays in terms of both the source of an X-ray and the different properties of an X-ray, as they're going to have a major connection to the Compton scattering experiment. Learning outcome is to explain qualitatively and quantitatively the Compton effect as another example of wave-particle duality, applying the laws of mechanics and of conservation of momentum and energy to photons. Okay, so we're going to start off with looking at a small experiment performed by the scientist Wilhelm Röntgen. And you'll notice a common theme throughout this unit where we do tend to talk about a lot of physicists and the experiments that they did perform. So in this case, what we have is once again our cathode ray tube. But what Röntgen did is he performed a cathode ray tube experiment, but did it at a much higher voltage than what we are used to. So just to draw the comparison to the photoelectric effect, the photoelectric effect, we actually have no voltage source. The energy is being provided by the light that you're shining on the cathode. So in this case right here, now we're back to actually having a battery. So I could draw that on here where I have, here's a little wire. And short end of the battery is a negative terminal, long end is the positive terminal. We'll just connect that to the anode, and then we have a potential difference, delta V, across the battery, and we have a really, really high voltage going across. Now, what Röntgen noticed is that when you do this, this causes a fluorescent screen to glow. Now, that shouldn't be too surprising because when we actually looked at cathode rays earlier, we had a phosphorescent screen inside of or a screen coated with phosphor within the cathode ray tube, and then the electrons cause the screen to glow as they jumped across the tube. However, what Röntgen noticed is that even if you take the screen, and let's say we put it over towards the left here, and by left I mean right. So we have my screen, and it's coated with, it's a fluorescent screen. And even if the screen is outside of the cathode ray tube, it still glows. In fact, if you take a piece of black cardboard and you put it between the cathode ray tube and the screen, it's kind of like that, you can still make that fluorescent screen glow. So even by putting an opaque object between the fluorescent screen and the cathode ray tube, it's still having some kind of an effect on the fluorescent screen, which means that there's something from the tube that's passing through your piece of cardboard. Now, Röntgen wasn't sure what this was. He suspected it was some kind of form of radiation that the tube was emitting, although because he wasn't sure what the tube was emitting, it was a bit of an unknown form of radiation, he just called it an X-ray. So the X in X-rays is just making a reference to some kind of unknown quantity, I suppose. I'll come back to discussing the image of the person's hand a little bit later and talk about some of the other properties of an X-ray. Okay, so what's the source of an X-ray? Well, let's take it a step back for a moment and just talk about the source of all electromagnetic radiation. So I'm hoping at this point that if I did ask you what is the source of all electromagnetic radiation, and X-rays are a form of electromagnetic radiation, you would be able to tell me that the source of all electromagnetic radiation is an accelerating charge. Now, there's different ways that a charge can accelerate, but nonetheless, if you're going to produce EMR, an electromagnetic wave, it needs to come from an accelerating charge. So in terms of how we produce an X-ray, X-rays are produced by the rapid deceleration of high-speed electrons as they strike the anode in a cathode ray tube. And when the electrons strike the metal target, which would be the anode, the kinetic energy of your electrons is converted into photon energy or X-ray energy. So let's look at this illustration. This is kind of like a little bit of a backwards setup. So this part here, this would be your cathode, and your cathode is your negative side. And this other side here would be the anode. And what's happening is, let's do it with a different color. Let's do green maybe. Okay, so in the cathode ray tube, you have an electron that is going to jump across the tube. And what happens is the electron is just moving really fast. When it strikes the anode, it's going to slow down. It's going to accelerate in the reverse direction, or I guess we could use the loose word deceleration, although it's not ideal to describe something in terms of deceleration. But that's where the accelerating charge comes from. You have the electron, when it strikes the anode, it would accelerate in a direction opposite to what it was originally moving. And that acceleration is what produces your EMR. And it turns out, just like for the photoelectric effect, we're going to have that one-to-one rule, which means that if you have one electron that goes across the tube and strikes the anode, it's going to emit one X-ray photon. If you have a second, and by the way, there's going to be like way more than one electron going across the tube, but if you have another electron go across the tube, so we, I suppose, increase the intensity of electrons going across the tube, then we would produce another gamma ray photon. Okay, so each electron produces one gamma ray photon. And once again, this is where we need to use the wave particle nature of light to explain, focusing on the particle nature. So the particle nature is all about looking at light as being a discrete unit. So if one electron produces one photon, two electrons produce two photons. Again, we're very much looking at that particle nature. Now, I'm just going to show a little bit of an energy conversion that's occurring in terms of like, where does the energy start and where does it end up? So we have this cathode ray tube hooked up to a high potential voltage source. So that's your battery. That high potential voltage source does work to make electrons move across the tube. So that potential energy is used to accelerate electrons across the tube. Therefore, the electrons get kinetic energy. And then when one of those electrons strikes the anode, it decelerates or accelerates in the opposite direction, and that produces an X-ray photon. I sincerely doubt that it's perfect energy conservation, but we're just going to go along with that for the time being and make that assumption. I can break this equation down a little bit, because what's the potential energy from the voltage source? Well, it's Q times delta V. Again, we looked at that equation back in the electric forces and fields unit of study. The kinetic energy of the electron would be 1/2 mv squared. And the photon energy would just be h times f, or it could be hc over the wavelength, depending on what you are trying to, depending on whether you want to express it in terms of frequency or wavelength. Now, a few properties of this, we're going to break it into the two different parts of the X-ray photon, its wave nature and its particle nature. Let's look at the wave characteristics first. The wave characteristic of an X-ray is you have the ability for it to pass through objects such as wood, paper, aluminum, and human flesh. So X-rays can pass through opaque objects like that black piece of cardboard. However, if materials are really, really dense like bone, then they cannot pass through it, but they are allowed to pass through some opaque objects. And that is a wave characteristic. If you thought of it in terms of a particle I might think of like a marble. And if a marble strikes like a piece of cardboard, it just hits it and reflects off of it, as like a wave can actually pass through it. Two, It is possible to diffract an X-ray. It's just not easy. Again, the issue we have with diffraction is that in order to diffract light, you need to have a slit separation that is like really, 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 or not slit separation, but the spacing or the size of the slits, that's very tiny. It's got to be smaller than the wavelength of the light itself. The problem with an X-ray is an X-ray has a wavelength that is very, very small, which means that if you want to diffract an X-ray, you're going to need a slit that has a size that's also super, super small. So our Young's experiment, where we had the double slit or even a diffraction grating, that's not small enough to cause an X-ray to diffract. It turns out that just the atomic structure in certain crystals actually does have a natural diffraction grating built into it, and the size of those slits is small enough for the X-ray to diffract. Particle characteristics. X-rays can ionize gases and water. And again, just to kind of explain what it means to ionize a particular atom. So look like a really simple atom. So let's say we have just hydrogen, which has just the nucleus with one proton, and then you have an orbiting electron. So the E negative. Let's draw this around in a circle. Okay, so the reason this is a particle characteristic is if you have an X-ray photon and it actually approaches this electron here. Again, a photon is an energy carrier. What it can do is it can transfer energy into the electron, and the electron will get enough energy where it actually wants to leave the atom. So this electron would then go away. So you've ionized the atom or the molecule, whatever you're looking at, and that leaves it with a positive charge. Now, the reason this is a particle characteristic is because the only way you could actually have, and this is the key word here, a collision. So there's a collision between the electrons, the photon and the electron, is that you need to look at the particle characteristic of light, and that deals with momentum. Momentum is the principle we deal with whenever we're looking at collision between objects. Now, this seems to be a bit of a contradiction because once again, well, how does a photon, which is a massless, chargeless particle, have momentum? It has no mass to it. However, this can happen. If a photon, X-ray photon, does hit an electron, it can make it leave the atom, and the atom is positively charged. So we've got that momentum particle characteristic. Okay, second point is that X-rays can affect photographic plates. Okay, so let's go back to this previous slide of like the X-ray of a person's hand. Maybe just briefly explain how this actually does work. Okay, so let's say you were taking an X-ray of like a person's hand. So let's just use this purple thing right here as the screen. And we'll say this screen is what I'm going to call a photographic plate. Okay, and this photographic plate is white. What we're going to do is we're going to put an object that we want to X-ray in front of it. So let's say we had like a piece of a bone, but again, since I can't draw, I'm just going to draw this bone as a rectangle because I'm pretty good at drawing that. That's a pretty good rectangle for a drawing tablet. Okay, so let's say that's a piece of bone. Okay, and then we start to fire X-ray photons at this. So what happens is, so I'm going to just represent the X-ray photons with rays of light. So let's say we have like a ray of light that is going to shine here. If an X-ray photon hits it, it just gets absorbed. X-ray photon hits it, gets absorbed, doesn't pass through. Okay, and then once you have X-ray photons that can actually not get absorbed by the bone, what they do is they just cause the screen there to turn black. Okay, so I'll draw it a few spots down. Let's get black here. Okay, so if the X-ray strikes the photographic plate, it causes it to turn black in color. Strikes the plate, it causes it to turn black in color. So what you're actually seeing in an X-ray is it's showing you the spots of where the X-ray is not hitting the photographic plate. The spots where it's not hitting the photographic plates continue to be white. So in a sense, it's kind of weird. It's almost like what an X-ray is doing is it's like a shadow in the sense of like your hand, except instead of the shadow appearing black in color, it's actually appearing white in color. I would say this is a particle characteristic because when you're looking at the X-ray firing around the bone, it's not really diffracting around the bone. It's not changing direction. It's pretty much just moving in a straight line. And in a sense, it's kind of like forming a shadow of like what the bone does look like. So I would classify that as being a particle characteristic. Okay, so now we get into the Compton effect. And another scientist, Arthur Compton, he both predicted and confirmed with an experiment that a photon does have momentum. And again, let's address the problem with this statement. So this equation would be the equation for the magnitude of the momentum of an object. So your momentum P is equal to mass times the speed of the object. We'll call that equation number 1 or equation star. The problem we have is, well, how can you calculate the momentum of a photon if it doesn't have any mass? Well, we're going to kind of cheat around this right now. And the way we're going to cheat around this is we're going to use an equation in physics that's really, really famous, although perhaps not a lot of people understand like the significance of it. And we're going to deal more with this equation in the last unit of study on nuclear physics. But that equation is E equals mc squared. What this equation is, and again, I'll talk about it in much more detail later, is it's Albert Einstein's energy mass equivalence equation, which tells you in some situations it is possible, this is not easy to do, you can take pure energy and turn it into mass, or you can take mass and you can convert it into energy. And the speed of light squared is kind of like a conversion factor between them. And again, this is not easy to do, but it is actually possible that you can take like an energy from like a gamma ray and you can actually form mass out of it. Again, it's just really hard to do it. So we're going to do a little bit of a cheat with the equation here. So the cheat with the equation is we're just going to manipulate this for m, and we'd have m is equal to E divided by c squared. This equation would be what is the mass equivalent of a photon, which pretty much means if you could take the energy of a photon and turn it into mass, this is how you would do it. Now, that doesn't mean that a photon does have mass. It just has a mass equivalent. Kind of like, again, the hypothetical in terms of if you could actually take the energy of a photon and turn it into mass. But again, we're just going to use the equation as a cheat to get around this for the time being. Again, we'll come back to this principle of conservation of mass energy much later on. Okay, so I'm going to take equation 2 and sub it into 1. And when I do that, I would then have P, which is the momentum of my photon, is equal to E, the energy of the photon, times its speed, divided by the speed of light squared. If we have a photon that's in air or a vacuum, then its speed is pretty much just the speed of light. So you can replace the V with the C. Cancel those off. And then if I manipulate the equation for E, this is a way you could calculate the energy of a photon from its momentum. So you take the magnitude of a photon's momentum and multiply by the speed of light. It's another way to calculate a photon energy. On top of the other equation we already have, we already know that E is equal to H times F, or Hc over the wavelength. We're going to take this a step further, though, because what I want to do is I want to get an equation for the momentum of a photon. So let's manipulate this again. Let's go a step back where we have P is equal to E over C. And what I'm going to do is I'm going to plug in for E, the energy of a photon, the Planck formula for calculating a photon's energy, which is Planck's constant times the frequency. When I do this, if you take this part of the equation, which is F over C, that's just a variation of the universal wave equations. The universal wave equation is V is equal to F times the wavelength. And if you manipulate it for, if we went F over V, you'd have F over V would be equal to 1 over the wavelength. So what we can do is we can replace F over C or F over V with 1 over wavelength. And this gives me an equation for the momentum of a photon. So the momentum of a photon is Planck's constant divided by the wavelength of a photon. Okay, both these equations are on the formula sheet, but there is something I wanted to point out about this equation. So do all photons have momentum? Yeah, technically they do because they all have a wavelength to it. However, only certain photons have any momentum that's even worth considering. In order for the photon momentum to be even remotely significant, what you would need, because there's an inverse relationship between P and lambda, is that you would need lambda to be really, really small. If lambda is small, then your momentum can be bigger. So really, when we're talking about the momentum of light, it's really only a big deal. When I say a big deal, I mean a big deal like the quantum level, where like we're looking at really small things. Like I don't think you need to worry about like taking a step out into sunlight and suddenly being pelted by visible light photons and knocking you over. Like you're not going to notice anything. But the only photons we really care about for momentum would be X-rays and gamma rays. They can do things at the subatomic level. When I say the subatomic level, I mean like interacting with like electrons.
Bob, can you call 2403, please?
Mainly just electrons. Okay, so this is the prediction that a photon has momentum, and it can be calculated by h over lambda. And then Compton also, not only did he predict this, he also conducted an experiment to support this idea. And the way he tested it is, okay, I want to see if a photon has momentum. So how do you figure out if something has momentum? Well, it needs to be able to induce a collision. The problem is, like a photon, I mean, it does have momentum and not much. So again, like you can't take an X-ray photon and fire it at like a tennis ball and make it move. It's not going to happen. You might be able to shine it at something that has a very small mass and get it to move. So specifically what we're going to do is we're going to take a photon and fire it at an electron, because an electron has a very, very tiny mass. It's around like 10 to the negative 31 kilograms. So the setup of the experiment is like, it's actually pretty simple. I suppose from like, if you don't think about like all the small details of the experiment. So really all we're going to do is we're going to take an X-ray photon. We'll call it the incident photon of light. So we have lambda I, or you could call it lambda 1 if you wanted to. And then I'm going to fire at an electron that's at rest. And what I'm trying to do is just see if I can observe a collision. This is pretty much the same thing as the lab that we did in class dealing with the air table, where we took like one puck and just launched it at a stationary one, and we tried to create that collision where the two things spread apart. So all we're doing is if we fire this X-ray photon, and if that electron moves, that tells me that a photon must have momentum. So Compton went ahead and did this, and yeah, it can actually cause the electron to recoil or move a little bit. I did mention that part of the experiment was that he measured the wavelength of the incident light and the wavelength of the photon that's leaving. So that would be lambda F. And then also the angle on which the photon is being scattered at. So basically these three things we're kind of looking at, and also just trying to see if we can actually observe that electron getting bumped around. Okay, so the results of this experiment is Compton actually confirmed that this collision is elastic. Now, just as a quick reminder, in case you've forgotten what an elastic collision is, okay, an elastic collision is one where both your net momentum and your net kinetic energy, so sigma ek, are conserved before and after a collision. Although I don't think we're going to say kinetic energy here. We're just going to simply say it's going to be your net energy is going to be conserved. So just your sigma E is going to be conserved. Because it's a little more difficult to talk about the kinetic energy of a photon. Like, yeah, photons are always moving, but we'll just call it photon energy instead of kinetic energy. I believe I mentioned earlier on that 99.9999% of all collisions would be inelastic. So inelastic means net momentum is conserved, but not your kinetic energy. The reason being is in almost every collision, either you're going to lose some energy in the form of sound, thermal energy, or just in deforming the objects when they contact. So this would be like the one situation that we can say is elastic, where both net momentum and net kinetic energy is conserved. So again, elastic collision means that energy is conserved. So again, if we go back to our little diagram here, we're shining a photon of light. I don't know why the picture is showing it as a continuous wave. I would just show it as like single little photon here. And then you're getting a scattered photon, and the scattered photon does have a larger wavelength to it, and I'll talk about that in a moment. Fire out an electron, and we observe this collision. So if we look at conservation of energy, we could say that the energy before the collision is equal to the energy after the collision. And let's let 1 equal the photon and 2 be the electron. So if I broke this down, the energy before the collision would be the energy of the photon before plus the energy of the electron before, and that would be equal to the energy of the photon after plus the energy of the electron after. Initially, we're making the assumption that the electron is not moving. And if we break this down a little bit more, what we would have is, if you want to write down the photon energy in terms of wavelength, it'd be hc over the wavelength. So if hc over lambda I is equal to hc over lambda f plus 1/2 mv squared. So that's an equation we could use to deal with Compton scattering problems from a conservation of energy perspective. And you'll get to practice this on one of the homework assignments. With that being said, if the collision's elastic, it also means that momentum is conserved. So let's look at this from a momentum perspective. So we'd have the net momentum before is equal to the net momentum after. So the net momentum before would be the momentum of object 1 before plus momentum of object 2 before, and that equals momentum of object 1 after plus momentum of object 2 after. Once again, the electron's not moving before the collision. How that is possible, I do not know. So we'll just pretend that it isn't moving. And then we have momentum of object 1 before equals momentum of object 1 after plus momentum of object 2 after. The problem with momentum in comparison to energy is, if you ever had a choice between using conservation of energy or conservation of momentum and dealing with one of these scattering problems, I would always go to conservation of energy first. The reason being is conservation of energy deals with scalars, so we don't have to worry about the actual direction. Momentum conservation deals with vectors, which means that if you wanted to properly analyze conservation of momentum, you'd either have to do it through vector addition, or you'd have to set up a triangle. So if we look at our picture here, our momentum of object 1 before points towards the right. After, the momentum of object 1 is down to the right. Electron is up and towards the right. We can construct a resultant vector diagram based on this, and we'd have to use something like a sine or a cosine law to solve for an unknown quantity. Or you could also solve it using components, where you'd have to look at the sum of the momentum in the x direction and the sum of the momentum in the y direction. So for energy, you don't have to do that, which makes using energy a lot easier. Now, it's not to say that like you'll always have that choice. You might at some point have to deal with a problem where you do need to use both principles. So it's important to know how to use both of them. And what I'll do is I'll attach a scanned Word document of a problem where I show the solution for both conservation of energy and conservation of momentum. And you can see how much more difficult it is with conservation of momentum. Now, one other thing I want to point out is that the wavelength of the photon after the collision is bigger. Well, why is that the case? Well, think of it like this. This photon, whatever energy it has, it's going to give some of it to the electron. Therefore, whatever energy this photon has in comparison to originally is going to be a little bit lower, okay? Because it had to lose some energy to give it to the electron. So what does it mean for you to have a lower photon energy? Well, it means you either have a higher frequency or you have a lower wavelength. Other way around. It means you either have lower energy is going to be higher frequency, and lower energy would be, oh my goodness, I just said the same incorrect thing twice. Okay. Third time is a charm. I don't know if it is actually a charm, but I'll just pretend like it is. Okay. If your photon energy is lower, then your frequency is lower. If your frequency is lower, your wavelength is bigger. There we go. Okay. Got it that time. So this photon gives some of its energy to the electron, which results in this photon having less energy, which means it has a smaller frequency but a higher wavelength. Okay. You have no idea how difficult it is to record one of these videos without saying something stupid for 30 or 40 minutes, which gets me thinking, like when I actually do a lecture in class, how many dumb things I say within like a 30-minute span in every single lesson. Okay, one other equation and thing that Compton did is he derived an equation for the change in this wavelength of the X-ray photon. So again, we've already identified the wavelength is going to get bigger because the energy gets smaller. So the equation, I'm not going to show the derivation for it, tells me that the change in the wavelength of your X-ray photon is equal to h over mc multiplied by 1 minus cosine of theta. In this equation, m is the mass of an electron, and theta is the photon scattering angle. So not to be confused with the electron recoil angle. And just one other thing about the equation. So if I said to you, how could you maximize your change in wavelength? So what could I do to make the change in wavelength a maximum? Well, this is all going to depend on what the angle theta is. So the question here is, what angle of theta could I plug in that would result in 1 minus cosine theta being a maximum? Because Planck's constant is constant, obviously. The mass of an electron is constant, so is the speed of light. So it's all about this angle theta. Okay, well, cos of 0 degrees would be 1, so that is not going to work at all, because cos of 0 is, take a look at this, cos of 0. Oops, that's just, let's look at cos of theta. And cosine of 0 degrees, I believe, is equal to 1. Okay, so what that would do is that would make 1 minus 1 equal to 0. There is no change in wavelength. So what that would mean is basically the photon just, you fire it at the electron. And then if theta is 0, it just means that it would just continue going in the exact same direction. If it keeps going in the same direction, it means it had no interaction with the electron at all. So nothing should have changed. Its energy should not have changed at all. Well, how about cos of 90? Cos of 90 degrees would be 0. So that would be 1 minus 0, which is just 1. Okay, so then the change of wavelength would be h over mc. So that would be like if the photon was fired here, and then after the collision, it went at a 90-degree angle to where it was going. That's still not quite the maximum, though, because it turns out that if you take cos of 180, cos of 180 degrees is negative 1. And then you would have 1 minus negative 1, which would give you 2. So that would be the biggest way that you could maximize the change in wavelength. So what would this be? That would be like taking a photon and firing it, and then a 180-degree angle means it just bounces back along the exact same line. And that's going to result in your largest change in your wavelength. Okay, we're actually going to break the assignment up into 2 parts because the next lesson I'm going to do is going to be all theory, but I'm not going to have any assignment for the theory until later. So we'll first of all focus on the X-ray parts of the lesson with the assignment. And then the next lesson we'll talk about the different spectra of light, and then I'll assign problems dealing with the Compton effect then. And I will talk to you in that next lesson.